Okay, we're going to talk about longitudinal control and trim today. And everything we've been looking at so far, CG was critical. As we move the CG farther away from the neutral point, control becomes critical. Okay, so they are opposites. Like I say, early on I've said in this class that, when we say stability control, we say it all in one breath. And that makes people tend to think that they're the same. Well, they're not. They're opposites. Okay, a very controllable airplane is not a very stable airplane, and vice versa. So, as we march that center of gravity forward, the airplane becomes less and less controllable. And you can get to a point where you can't control it at all. It's a lawn dart. Okay, that it's going in the direction that it's going in. And that has to do with center of gravity. So you might imagine then that from the control standpoint, there's a limit on the forward end. And it is set by control. Now, for years, there's been several different things that the authorities have looked at from the standpoint of control. One of them has been, can you raise the nose gear if it's a tricycle gear airplane? Can you raise the nose gear from the runway in time before you run out of runway? So you can get an angle of attack so the airplane will take off. So nose wheel liftoff has been a thing. For years, the FAA for small airplanes did not have a requirement that you had to measure the takeoff distance. One of the reasons was takeoff distance is very dependent upon the pilot and pilot technique in the takeoff. And the FAA considered in their early days that most pilots, you couldn't, you got 10 pilots and you got 10 different takeoff distances. So they said, why are we bothering to measure this? If the airplane will climb, we can measure its rate of climb in the takeoff configuration. Then we won't bother with it, but we'll also see if it is capable of raising the nose gear so we can get an angle of attack. So anyway, that's the kinds of things we're going to talk about this morning, or this afternoon. So the most aft CG limit normally is determined by stability, and the most forward CG limit is by control power. Now, in ground effect, the downwash at the tail is reduced, and that requires additional up elevate. Now, those of you who are learned to fly probably have noticed that when you're coming in for a landing, you're all set up and you're coming in with a nice glide slope, and as you get close to the ground, you need to more up elevator to maintain the same flight path. What's happening is you're coming into ground effect, the downwash is hitting the ground, the flow is hitting the ground and reducing the angle of attack of the tail. And remember, it's always down, in spite of the fact that us college professors always draw the damn thing in the wrong direction. We always draw the lift of the tail up. Lift of the tail is down, And I can tell you that I've spent some time in an airplane without a tail. It's not a lot of fun. But when the tail comes off, the airplane does this. Someplace about right there, the wing will fail. And then it really gets to be a wild ride, okay? But, anyway, I'll get off of my soapbox here about airplanes and tape. But that download is down, and I get back to what I was talking about. We're coming in here with our airplane, and here's the, as we get into ground effect, which is about 1 wingspan. Okay, as we get into ground effect, we have to increase the elevator because of that change in the downward tail in order to land the airplane. So that's another case for control, right? Because we don't want to do this. We want to be able to flare the airplane and make a nice soft landing. Well, the CG location affects the ability of the trimming device to trim out longitudinal control forces throughout the CG range. If you keep moving the center of gravity forward, eventually you can't trim the forces to 0 on the control wheel. You'll have to hold some. Now, the Federal Air regulations allow up to 10 pounds of out of force. And that, you know, once you get to 10 pounds, that's going to set the forward limit. Well, FCG, however, is critical for high-speed trim. If we load the CG airplane way aft, we have to reduce that tail download to the point of where it will do it. And we do that by changing the trim so it will float there. So when we fly this particular flight, and we're going to do that, by the way, we're going to fly this flight next. And if you look at your schedule, it's not set up by the way, but we're going to fly this flight next rather than lateral directional stability, because I haven't talked about lateral directional stability yet, okay, one of our reasons. And we'll probably do this one after spring break. But anyway, so when we do this flight, 2 of the groups will fly it forward CG, since that's where more of the things are, but one of the groups will fly it aft CG, so you can see if the airplane, and it's about trim and level flight. Again, the rules require that you be able to trim, hands off, to 0.9 times the maximum level flight speed, and that speed is called V sub H in the rules. And V sub H is determined at sea level, and you must be able to, at gross weight, and you must be able to trim to 0.9 times VH. Okay, so you don't have to trim all the way to max level flight speed, but you have to trim near it, according to the rules. Now, one of the things you want to be careful of in doing an airplane is that you just want it to barely meet that requirement. And here's the reason why. If you then move the CG forward, or if you're flying at another CG other than half CG, and you can trim way beyond VH, then what will happen is people will be able to trim beyond the red line. Not a good plane. Several years ago, when I was at UT, I was going to Dayton, Ohio for some reason, and it required about 3 different commuter rides to get there from Nashville, Tennessee. And I was in this commuter, and I think I was about the only passenger. And the crew was flying, and we were going into some place in Kentucky. And I looked up there, and they're descending above the red line. Well, guys, you know, you got me on board here. I don't want to be up there. And I guess they had gotten by with this for some time, but you know, and if you end up as an airline pilot sometime, be careful who you have on board. They they may know what's going on. But anyway, okay. Well, it's desirable to keep trim changes with configuration change as low as possible in order to improve the longitudinal flying qualities of the airplane. We have just had some research here. Somebody that you know who usually runs the camera. Tizzy is doing this particular thing for his thesis. And what we've discovered is that many general aviation airplanes, when you make a configuration change, like put the flaps down, if the pilot doesn't retrim the airplane, hold the force and retrim the airplane, if he just lets it go and puts the flaps down, many general aviation airplanes will do this.
I got those slides, I'll bring them up while you're talking.
Okay. And when they do, well, the airplane will go to a stall, and if the pilot is distracted, it may depart control flight. Well, when do you normally put the flaps down? In landing, right? Approach and landing, you normally put the flaps down. And so at that time, you're 1,000 feet above the ground at most. And if the airplane goes up into a stall, you don't have a lot of time to recover. For years, almost since the Wright brothers, maybe since the Wright brothers, we have been looking at how to solve the quote-unquote stall spin problem. Well, from my own experience, I know that if you do a stall with a one-turn spin, which was the requirement in the FARs, for a non-spinnable airplane, okay, that if you stall and do a one-turn spin and recover, number one, it's going to take 8 to 1,200 feet of altitude. You're going to kind of pull about 3G on the bottom, and you're going to hit about 120 knots with most light airplanes. At least today's light airplanes. Now, back in the Cub and Champ days, you could get by with a good deal less than that. But we say pattern altitude's 1,000 feet. Even if you recover, you're going to hit the ground at 120 knots. Might spoil your whole day. Okay. But we spent a lot of time, folks at NASA back in the 70s spent all kinds of people's tax money trying to solve this quote-unquote spin problem. Didn't matter. The accident rate from so-called, now we call it loss of control, the accident rate has stayed at around 45% of total accidents. As long as I've been doing this, and I've been doing this a long time. And so my thought was, wait a minute, we don't want the guy to stall, or girl to stall in the traffic pattern because they're going to die. Pure and simple. So what do? Well, we got to back up and find what's causing them to stall in the first place. One of the things that I began to look at some years ago was this issue of configuration change, because that's one of the things that you're doing in the traffic pattern. You're putting gear down, you're putting flaps down, all of those kinds of things. And if you get distracted and the airplane does something strange, like pitch nose up, it sets you up. And so that was why we started this project. Okay, take a look at some of these. We've actually done 4 different airplanes. And we tried not, we had available a number of Piper airplanes and one Cessna airplane, the 172.
That's all the stick forces we measured.
And these are the stick forces we measured over here. And notice, they're all push forces for the most part. Which, when you put the flap down, it means you've got to do this sort of thing. And notice how big some of them are. 20, 36, 26, 29. Okay. That's a pretty healthy force. Now, here's what the Federal Air Regulations allow. Originally, they allowed 75 pounds. 75 pounds. Do that with one hand someday. And see how bad you shake. Trying to do it with your left hand in particular. Now they've reduced it a little bit. It's 60 pounds. None of these airplanes are anyways near 60 pounds. Yet, you can see what they do. Notice what happens to the airspeed when you do these changes. Notice that only one airplane, and this is the Ph.D 180 airplane, there's only one airplane that does what it probably ought to do, and although it has about a 10-pound nose-up force, but it seems that 10 pounds won't drive it to stall. But anything above that, it does. All of these other airplanes have that, including an airplane that's somewhat like the 180. Except, someplace down the road, Piper decided to make the tail on the Warriors and all those airplanes bigger. In fact, the Cherokee 180 that I own, and it's sitting out at the airport right now, tail is 40, span is 40 inches less than the Warrior, which actually has a lower gross weight and what have you. But notice that all of them, when you put the flaps down, except for the 180, all of them pretty much follow the same path in airspeed. This means that the nose is coming up and the airspeed is coming down. This is pitch attitude, and looky what happens. It goes to up around 35 degrees of nose-up pitch attitude. Now I can tell you, 35 degrees sitting here in the classroom don't seem like that much. When you're in the airplane and it goes up to 35 degrees, you think you're going on your back. In fact, it was I was a pilot on these things, and it was almost impossible to resist putting some force on there to keep the nose down because the nose was going up so fast. Yeah, maybe we're going to see the video here, I guess. And all I'm trying to do here is just keep the wings level.
Is there sound to it? Because I got my sound all the way.
And now
There
there's
you go.
no.
Here comes the flaps.
Tell you what happens to the nose here. How you're looking at the sky. And then the airplane stalls and down the nose comes. Trim change with configuration change, big in this case.
You get the wing view.
Yeah, get the one out the side view. Here we go, we're flying along. You can tell when the flaps come down. Now, the thing about the Cherokees is you got this big bar that you put the flaps down with, so you can put them down fairly fast. But what we found, the Cessna has an electric motor, and it departs just as fast.
If this is the right clip, I may have grabbed the wrong clip. Let's see.
There it
is.
goes, there it goes, there it goes. Now notice, if I hadn't got into the act there, it would have probably departed control flight. So, we want to keep those trim changes as low as possible in order to improve the longitudinal flying qualities of the airplane, because we don't want, when the pilot has the airplane trimmed originally and he makes a configuration change, we'd like the airplane to essentially maintain that airspeed. Okay, so that's an important thing, and it has over the years it's been overlooked. Now, if we look at the regulations, you'll find in the regulations for longitudinal control, there's a maneuvering requirement, a takeoff control requirement, and a landing control requirement. And if you look in the military specifications, they contain all three of those. Mil-specs, the FAA regs, on the other hand, only contain the last two because the FAA doesn't care too much. The military cares about maneuvering, because if you're flying a fighter, you want to be able to really honk it around. Cherokee, you don't care about honking it around that much, okay? So, FAA regs only contain a takeoff requirement and a landing control requirement. Now, in recent years, even some of those have came out of the regs, and they inserted, instead of the takeoff control requirement, which was the nose wheel liftoff requirement, they inserted measure the takeoff distance. Now think about that a minute. Measure the takeoff distance. They didn't say what it had to be. Just measure it. Well, let's see. It took from here to Orlando to get airborne. And we measured it. That wouldn't be a very good airplane, would it? It took from here to Orlando for it to fly. But that's what the rule says. And they took out, before it said you had to lift the nose wheel at 0.9 times the stalling speed. That was a maximum at, 0.9 times the stall speed. You had to be able to lift the nose wheel before that. Well, that came out of the regulation recently, and in its place they said measure the takeoff distance. Well, both the military and the FAA regs contain requirements for the longitudinal trim. Well, control, of course, is the function of elevator deflection of available and longitudinal stability. We said as the farther forward we go, the more stable the airplane is, which is a function of center of gravity. And the airplane should be able to achieve maximum lift coefficient at its forward CG position in order to achieve the lowest stall speed. Since most all of the requirements are based on some multiple of stall speed. And it's been found that the fatality rate goes up as the stall speed squared. So the higher the stall speed, the more people get killed in this business, okay? Is essentially what it says on an airplane. Of course, military fighters, you also want to be able to achieve CL max maneuvering at the most forward center of gravity. Because if you run out of control and there's some guy trying to shoot you down, you want to be able to outturn him. And that's a direct function of CL max. Well, the most forward CG position where CL max can be achieved is shown in this plot here. So here's the CG position, kind of thing we've been dealing with, right? We've been recording the elevator deflection with CL. And remember this guy, it all comes from one point, right? D delta E CL equals 0. Important thing. But anyway, notice that, hey, so this is 30% Mach on this imaginary airplane. Here's 20, here's 10. And we can only achieve CL max right here at that elevator deflection. Well, that's probably going to limit our CG on this imaginary airplane to about 18% of the mean aerodynamic chord, if it was like that. So that's how you would determine this. You know, you're going to have these plots from doing the longitudinal stability for the most part, and you can extrapolate where that's going to be. Now, during takeoff, in addition to the forces we have on the airplane in up and away flight, we've got one more, and that's this rolling friction, which is tending to keep the airplane nose down more. So we have to have a larger tail downward. Let's see. So we need sufficient control power to assume the takeoff attitude prior to reaching the liftoff speed. And it may be critical for T-tail airplanes due to rolling friction causing a nose down moment that the horizontal tail must overcome. Years ago, when I was working at Piper, our boss, who later became the FAA administrator, was a fellow by the name of J. Lynn Helms. And Mr. Helms decided he wanted to change Piper's image. He said that when people thought of Piper, they thought the next thing they thought was Cub. Piper Cub. And he said, here we are building all of these new modern airplanes, including turboprop airplanes at the time, and he said, you know, everybody, when they hear Piper, they think Cub, which was a great airplane, and still is, by the way, but, you know, he wanted to change the image, and so his approach to do that was to put T-tails on the airplanes. Now, I can tell you that the folks at Vero Beach absolutely hated it. It was not invented here for them, okay? And what you learn in the industry after a while, that NIH, not invented here, is a very big factor. Well, that was the case at Vero. But anyway, we put T-tails on the airplane to like them, our airplanes. What we found was that the T-tail has a lot of nice features, particularly in these trim change things that we've just been looking at, because the tail is way up out of the downwash, and so you can put the flaps down and it'll just maintain airspeed. In fact, one day I demonstrated over at Lakeland, went out in a T-tail arrow, set the trim for takeoff, flew around the traffic pattern, did touch and goes, and never touched the trim the whole time. And I was always in trim. Pretty nice, you know, that's the kind of thing you would like as far as flying quality is good. But folks at Bureau didn't like it. Okay. Anyway, and so eventually when Helms went to become FAA administrator, they put the tails back down. That's the history behind that. But anyway, the problem with the T-tails was lifting the nose wheel for takeoff. And that's why I told you that story. Same thing with a jet. With a low-tailed airplane, the propeller out in front, it's blowing air over that tail, so you can lift the nose at a much lower airspeed than when the tail is up out of that slipstream. Okay, in most cases, we can go out here and we'll probably do this when we do it. To do this particular test, you hold the brakes and you run the power all the way up and you have a control wheel back in your gut. And then you look at the airspeed indicator, and as soon as the nose comes up, that's the nose wheel liftoff speed. And on these airplanes that we have, it'll be close to instantaneous when you release the brakes with the low-tail airplanes. With the T-tails, that wasn't the case. And we had a hard time meeting the 0.9 VH in those days with the T-tail airplanes. But, like I say, tail still in landing, no problem. Where the low-tail airplanes, elevator required to land is the other thing. So if you're a very forward CG, and the Cherokee 6 was one of the airplanes that had this problem. If you have a couple people, just a couple folks in the Cherokee 6, and nobody in the back, that CG's way forward. It's actually the Cherokee 6 most forward CG is -3% of the mean aerodynamic chord. That means it's off the leading edge. Okay, that's the most forward CG. So when you come in to land in that configuration, you're all the way back against the stop. In fact, if you don't, on a Cherokee 6, if you or any Cherokee for that matter, if you pull it back and if you don't lift it up, you'll pull it back and think you're against the stop, and you're not. You have to actually lift the control wheel in order to get full up elevator deflection. And it takes that to land at the most forward CG for a Cherokee 6. You have to come back and that sort of thing to make it land. Right, without getting the nose wheel first. So, that's the problem we have. Now, the moment, of course, can be counteracted on a propeller-driven airplane by the slipstream. You know, the slipstream probably going to give us in takeoff configuration maybe 1.1 or so times free stream dynamic pressure. Well, in landing, the low-tail airplane, that's like 0.9 free stream velocity, okay? Well, flap deflection and creates a nose-down moment, except on airplanes that we looked at here today, where the downwash actually makes makes the tail have a higher download and helps you out. Now, what about airplanes where the little wheel is in the back? tail draggers as they are called, okay? Tail wheel airplanes. They are different enough that the FAA requires these days that you have to get a special checkout in order to fly them. Now way back when I learned to fly, that wasn't a requirement. Because there were a lot of tail wheel airplanes, okay, and a lot of people learned to fly in tail wheel airplanes. I learned to fly in a nose wheel airplane. I learned to fly, actually learned to fly in a jet airplane. And, well, let me tell you this. This is another story I'll tell on myself. I was a 100-hour jet pilot, okay? Really hot rock jet pilot, all right? And I had got checked out in a Ron-Ka-Champ in the local Aero Club. This is with Moody Air Force Base up in Valdosta, Georgia. And I'd got checked out in the Ron-Ka-Champ, which has the little wheel in the back. And when I got checked out, I had an instructor in the back. In addition to myself, I was flying out of the front seat and the instructor in the back, which moved the CG back, which, made the tail wheel, it would stay on the ground pretty well. And with the tail wheel on the ground, you have steering. But anyway, about 2 weeks later, I decided one nice sunny weekend to go out and fly the Champ again. So I went out and got in the Champ and flew up I-75 to Adel, Georgia. A lot of things in my flying career center around Adel, Georgia, particularly early flying career. Anyway, Adel, Georgia has a nice east-west runway. It's quite long, about 9 degrees to I-75. It's hard to see from I-75 if you drive up through Georgia, but it's out there. And then it has a short north-south grass strip. The FBO is located at the south end of that grass strip, and you can't see the FBO from the west end of the runway. So I entered downwind and we're landing to the east, so I'm going to touch down on the west end because there are nice big pine trees on both sides of the runway. So I, come down and I touch down, and the next thing I know, I'm going stop to stop on the rudders. And then the airplane goes, does a 270-degree turn on the runway, and, well, part of it on the runway, the rest of it off in the grass. And so I look out, and both tires are still on. Okay. Hadn't hit a wingtip or anything, so, and the engine was still running. I hadn't even hit the propeller or anything like that. So being a damn fool, I had power and taxied back down to the end of the, and nobody'd seen me. That was the important thing. Taxied back down the end of the runway and took off. It took me 5 more tries. I didn't ground loop every time because I had figured out that when things started getting out of hand, I'd add power and go around. But after a while, I began to wonder if I was going to be able to get the thing on the ground before I ran out of gas. Fortunately, I've after figured out what I was doing wrong. On that airplane with the little wheel in the back, particularly the forward CG, you had to have that control stick in your gut to keep the tail on the ground. So you had steering. Otherwise, tail got light and you didn't have any steering. And the next thing you know, like I say, you're going stop to stop with the rudders and nothing was happening. And the next thing you know, around goes the airplane. So, can present a problem in landing, especially at forward CG. And some sometimes you have to learn the hard way, and I guess I was one of those folks. Well, so for a conventional tail arrangement, the landing case is going to set up the elevator up requirement. For a T-tail airplane, that requirement is not so severe because the dynamic pressure at the tail is not affecting like it is on a low-tail airplane. And the ground effect at the T-tail is not quite as significant. The downwash doesn't change as much because the tail's up higher out of the high downwash area. So, in summary, the aft CG limit is set by stability. The forward CG limit is set by minimum acceptable controllability. Well, we would like to be able to trim the airplane for hands-off flight throughout its operating range, say from 90% of maximum level flight speed, and talked about that a little earlier, with the landing trim requirement being the most critical at forward CG. The maximum trim speed requirement is critical at most aft CG. So that's why when we fly this flight, two groups are going to fly forward because that's where we do the most things related to this particular thing. One group will fly aft to take a look at the problems at aft CG, okay? Now, it's rather interesting about how some of these things are done. I threw this picture in. This is a Mooney. The Mooney, you know, most airplanes have a trim tab. For instance, Cherokees we've been flying have a trim tab. Cessnas have a trim tab. Moonies move the whole tail. So if you see a Mooney at an airport sometime, go look at it and you'll see that right in here, there's a thing that this whole tail, there's a pivot that this whole tail moves. And up here on top, there's a slot that allows the tail to come forward, the vertical tail to come forward so you can trim it. And you'll find that there's no trim tab on the elevator. They trim the whole stabilizer and they do it by moving the whole tail. Some other airplanes you'll find have trimmable stabilizers. And this one, of course, has a trimmable stabilizer too. But some of them just move the stabilizer itself and not the whole tail, okay? And those are very powerful. In fact, they sometimes are too powerful. Here's a case. This is F-86 Korean War fighter. I had a good friend who flew F-86s, and he said they were the greatest airplane he'd ever flown. I've never flown an F-86, but I have flown a T-39, which used many of the components of the F-86. Notice this slot right here moves the whole stabilizer. This has a stabilizer and elevator. Now we know that most jet fighters today have an all-flying tail like the Cherokee 6. But the early ones still had elevator. You can kind of see the elevator line here in this picture on the F-86. Well, both the magnitude and direction of the trim changes may vary with center of gravity, so they're done at both forward and aft CG, and we did on this test that we did for Tizzy's thesis, we looked at both forward and aft CG on most of the airplanes. What we found was that there wasn't a large difference between forward and aft CG with configuration change. Aft CG being the worst case, but not a lot. And I'll show you these tables here. Here's what these tables rule. Notice that these changes over here You know, the first one there is glide, throttles closed, gear extended, flaps retracted, and then over here on the other end it says extend the flaps as rapidly as possible to the landing position, whatever it is, while maintaining approximately 40% above the instantaneous stall speed. And they want you to measure what that force is. Now, you know, this has been in the rule for a long, long time. But right before you read this part of the rule, number one, there is no requirements for force in this part. You just record it. If you read the rule prior to that, it allows now up to 60 pounds. Doesn't say which, these don't say which direction that force can be or any of that sort of thing. It just says you record the force. And essentially what you have here are things that you do in normal flying. It's forward and this is aft CG, I believe. Yeah, most rearward. So again, the same kind of things. So those are the two tables for trim changes for certifying a light airplane. And the FAA rules say the control forces for trim changes should not exceed 75 pounds for a light airplane. And that was the original. Like I say, they reduced that a bit today to 60 pounds. And 50 pounds for a transport airplane. Now wait a minute. A small airplane only has to have one pilot who can be a 100-pound weakling. Okay? But transport airplanes require two pilots. Two pilots. But they only have to exert 50 pounds of force, those two pilots. While the one pilot, the 100-pound weakling, has to be able to exert 75 pounds. What's wrong with this picture? We are in the process of rewriting the rule, and I happen to be on the committee that's doing it. And I keep raising a lot of cane about this particular item. Note that for military airplanes, those values are from 10 to 20 pounds. Why do they know that civil side doesn't know? I think they know a lot more. Okay. Well, airplanes with conventional tail location suffer large trim changes due to large changes in downwash and dynamic pressure per tail, with change in flap position and power. Some airplanes require interconnects between the flap extension mechanism and the trim. T-tail airplanes have an advantage in the air at trim changes. The trim changes are generally in the correct direction and small in magnitude.
That's the last slide.
And that's the last slide. Questions? Again, from the flight test standpoint, it's more interesting to see, and when we do this flight, we'll do some of these particular things. Whoever gets to ride up front, I'll let them experience some of these out of trim forces. Okay, questions? Let's see, next week is, no.
So we have class next
We
week.
got class next week, and we're going to spend the first class taking a look at, now that we've been through all the longitudinal stuff, and we find that, by golly, this airplane doesn't measure up. What can we do? And this is what happens in the flight test business, okay? In the flight test business, You know, designers have done all their stuff and this thing is just absolutely perfect. And then us flight test guys come along and say, nah, it ain't either. But if we're doing our job, we should be able to tell the design guys how to fix it. And by the time we get to the flight test, let me tell you, they are not going to, the company is not going to spend big bucks to redesign the whole airplane. Ain't gonna happen. So we start out, and we'll start out next time talking about simple fixes for some of these problems that we find in the flight test, on up to the more elaborate fixes. They will be expecting you, if you get out of the, graduate and go to work for a company in flight test, they're going to be expecting you to come up with some ideas when things don't work like they should. So that's the kind of thing we're going to talk about next time, about longitudinal. Okay? Have a good weekend.